एक ही है ना। आया था दुकान समझ में।
Okay. Hello. Am I audible? Can anybody respond?
Okay.
Okay. Thank you. I'll share the screen. Yeah, you can see the screen, right? Let me see if it is working or not. And it is 16th of March. Okay. So, good evening to all. Welcome to the class. So today we are, meeting for the third time. This third discussion, and we'll do some, basic winding up the lectures in the third week. Some special, insights, and then we'll practice some questions. So, what is the main idea of this week is to gain insights into reactivity of molecules, and especially we'll focus on acidic basic nature of molecules. So this course is focused in such a way so that first we'll understand the property of molecules, what governs the reactivity, okay, how you can design a reaction or how you know that certain reaction will work or not, okay. So for that we have studied, from the basics. So first we have studied, the molecular conformations, how a molecule look like, what will be 3D, three dimension, and then we went to conformational isomers, what are the factors for the stability. Then we went to the stereochemistry of this, okay, special configurations, how this will behave in different environments. And today we'll, brush up our concept about acidity and basicity, because these two concepts, like only one concept, acidity or basicity. So this is, governing the also the rate of your reaction, as well as how your molecule will behave. So whenever you are doing any organic reactions, they have different components. Okay, you can have substitution, you can have coupling reactions, you can have addition, you can have rearrangements. Okay, everything depends on your molecules. Okay, depends on compound or reactant, and especially on functional groups, what functional groups are present. So uh, these reactions, okay, certain, it has some certain time scale. So all the reactions have certain time scale. Okay, some reaction will be slow, some reaction will be fast. Okay, so how to determine that which reaction will, so the reaction which will be most favorable, that will happen first, then the next reaction will follow. So if you have something, pH of the system as governing factor, then it will lead to acid base reaction. Okay, and why it is important? Because it is typically faster than in other component reaction. Okay, that is why we need to take care about the pH, or the relative acidity and basicity of the reactants that we are using. Hmm. So you know to predict or uh, stabilize a system, adjusting the right pH is a must. Whenever you have some functional groups, such as I will go into detail also, you have some acid or some base kind of system. So each one having specific pK value. You have heard about pK values. Nevertheless, we will discuss it in the class also. So if your pH is less than your pK, then your compound will be in acidic form. Your pH is greater than your pK, compound will be stable in basic form. Okay, so in case your reactant is acid, but you have changed the pH less than, sorry, greater than, you have not stabilized the pH, so your pH is greater than pK, so your molecule is in this form. Okay, this ionic form. So this will not react. uh, it will not convert to the product. So that is why taking care of the pH is very essential. So with that, we'll just brush up this lecture of third week. So what we'll do, we'll estimate pK of some molecule. Second will be uh, reducing equilibrium constant for acid base reactions, and then uh, determining the factors for specific pK value, or stability, and then relative comparison between different molecules. Because if you cannot draw a comparison between different molecules, you cannot determine that in the same situation how this molecules is going to react. Okay, suppose you have different substitution on your compound. You have one methyl, one ethyl, or something, one phenyl green. So all this scenario, how your reaction will be, different. That things we have to study. So, known functional groups that we know that it is prevalent in the reactants, because functional groups are the group of molecules that govern that reacts in between themselves carry the reaction forward. Okay, these are the functional groups are responsible for carrying out the reaction. So what do you have? You have alkanes, you have alcohols. So like this general representation RCH2OH, you have ether, okay, RCH2O, CH2R, okay. You have thiols. Just if you replace O by SH, it is called thiol, okay, because of sulfur. So you have unsaturated groups also like alkene, then alkyne. What else do you have? Some halide. Sorry. Okay, X can be Cl, Br, I, or fluorine, right? Uh, you can have aldehyde, RCOH. Similarly, ketone, R, C double bond R. Then acid halide, acid halide, RCOX. Amines, amine can be primary R NH2, then secondary RNH R, or tertiary R3N. What else do you have? You have amide, okay, RCONH2. Then you have nitrile, so like this triple bond, and okay. And what are the types of acid? You have three concepts, okay, that are widely known. What are three concepts? First is Arrhenius concept. What does it tell? So in water medium acid will increase concentration of H plus, okay, or H3O plus. These two are same actually, H plus or H2 plus, because H2O normally couples up with H plus and then creates hydronium H3O plus. Okay, like HCl, if you dissolve in water, HCl plus H2O, what will happen? So H3O plus will generate, and then your Cl minus will stay. Okay, this will be the active species in the solution. So this is called acid. So similarly, if you take NH3 in water, what will happen? So here NH3 has some lone pair, so it will take the proton out of water. So water will stay as hydroxide plus NH4 plus, NH4 plus. Okay, so this is as it is, increasing the concentration of base, hydroxyl anion. So this is acting as a base in water. This is acting as an acid. So second concept is Bronsted-Lowry. What does it tell? This is also similar uh, compared to Arrhenius, but only difference is that it does not mention the specificity of water. So Arrhenius, you are specifically saying that in water medium. So Bronsted-Lowry doesn't tell that, but still, uh, acid will give proton that is H plus to form conjugate base. So here a specific term that is called conjugate base and conjugate acid also. So these two are discussed. So let me tell you. Suppose you have HA. This is a species and it is giving away your proton H plus and A minus. So A minus will be called as conjugate base, and the other species that already has given away that proton, it will be called as conjugate acid. Okay, this is the relation. So conjugate acid and conjugate base are related by proton. Okay, one proton. I think it is clear to you. Okay, so in this same scenario that we showed earlier, HCl plus water will have H3O plus Cl. So here Cl minus will be your conjugate base and HCl will be conjugate acid. Okay, like that. And then the third concept is sorry, that concept is Lewis. So Lewis acid is a species which will take electron. Species will be acid, Lewis acid, if it can accept an electron, and Lewis base can give away electron. So there are some species which doesn't have any proton associated. So how do you determine the acidity for them? So that is why this Lewis concept is introduced, so that compounds like I use some other color. Yes. Like BF3. Okay, then AlCl3. This kind of complexes. So you know that this has incomplete octet. Incomplete octet, and it can take electrons. That is why they are called as Lewis acid. Okay, you understand? So now let us move further. Okay. Let us move further. So now you have to think about stability, because in all our discussions we have considered stability of the molecule. It is very important, stability of acid base pairs, because if your molecule is not stable, okay, then there is no meaning of doing a reaction. Your reaction will not happen if your molecule is not stable. So let us see that how conjugate acid or conjugate base can be stable. So let us consider, there are many effects actually. Let us consider in this case you have a You have acid. Okay, so this is a carboxylic acid. So what are the protons you have? You have here 3 proton on the methyl. You have 1 proton on the oxygen. So there are two scenario. You can either remove this proton and then you can get to this formula CH3CO O minus, right? And in the other case, if you remove the other one, this one, then you will have CH2 minus, then OH. Now what you can see that in these two case, so you can have some resonance structures here. This negative charge can go on to the another oxygen atom. Sorry. Yes. Right? And it can come back again to here. But in this case, if you consider it the same way, CH2 double bond minus, then you have which, and it can come back and forth. But you have to think that this carbon versus oxygen. So negative charge will always, try to stay at the more electronegative atom. So this is more electronegative compared to carbon, that is less electronegative. So what happens if your negative charge is on such an atom which is more electronegative, it will be much more stable. So these structures are stable. That is why this proton that is close to the oxygen, it is much more tend to abstracted or to go out. Okay, so that is why this acidity, this proton acidity is much more than this one. So if you consider it as HA and HB, HA is much more acidic than HB. Okay, and this we actually denote by the term pKa. pKa is actually the negative logarithm of K. What is K? K is a acid constant. Acid constant. So how to get it? I will reduce it so that you can have an idea. Let me see. So for this reaction, Cl plus H2O, that is converting to H3O plus Cl minus, right? We have already discussed 2 times this one. So the equilibrium constant for this reaction will be concentration of the product, H3O plus, divided by what? The reactant concentration, HCl minus plus, sorry, not plus, this multiply. Okay, then H2O concentration. But as this H2O is a medium, this is a medium. So that concentration is much, much higher. Concentration is always much higher than other species. Okay. So this will be much, much higher every time. So let me take this one to other side. This one to other side. What will happen? K equilibrium into H2O concentration and Cl minus concentration, H3O plus divided by HCl reactant. Now this entity we consider as the Ka. This quantity we consider as Ka, acid constant. Okay. So from here, as you know, this value, this K value is a equilibrium constant. So then generally it comes in, 10 to the power minus X. So that will be very low value. And to gain useful value or number to, in calculation or for our use. So to gain gain an useful value, we use the term pk. So pk and ka are almost same, just it is a conversion, okay, taking the logarithm so that we can get a usual value. So it is not very much, useful to remember these values like 10 to the power minus 7, minus 9, not like that. So you can generally, remember the value 7 or 9 if you remember the pk value. So that's what pk is. Pk is negative logarithm of your ka value. Okay. So, uh, so there are differences in pk value depending on functional groups, right? So one thing that this pk value is related to the presence of proton. Okay, pka related to H plus concentration, right? So this thing you should remember it. Now, uh, so what are the different type of compounds we have that they are so much varying pK values? So compounds, I'll give you a brief idea. Compounds having different pK values. Hmm. So what are them? Let me list out. Uh, yes. So this I think already you have. It is already discussed in main classes. So H3O plus, that is hydronium ion. It typically has -1 value. Then you have RCOOH, that is your carboxylic acid. It has pK value of 5. Phenol, if you consider, it has pK value of 10. CH3OH, that is your alcohol. It is having 16. Water also has same 16. Then you have ketone CH3CO, CH3, it has 20. Then CH3CO, CH2, CH3, it has 10. R, NH, R, that is 35. R3, N, sorry, R3, NH. So nitrogen has 4, so it is positive. It has 10. And if you have any benzene adjacent to benzene or RCH2, then CRH, this proton it will be 40, and RC triple bond CH, this will be 50. So as I told you that pK is related to the proton. So which proton you have to specify it. So I will specify it. So H3O plus you have 3 proton, right? H plus. So any one of the proton will have this -1, and this 5 is for this oxygen proton, 10 is for this oxygen proton, 16 is for this one. Oxygen in water you have 2 proton. So any one of this will have this value. Then so in the CH3 you have 1 proton. So this proton value is 20, and this 10 value is for one of this proton. So you have 1 proton here. This proton will have 10 value. Uh, for the amine, it will be connected to the amine, nitrogen adjacent proton. Here also the same thing. This is adjacent to the benzene ring. And in this case, for sp2 hybridized carbon or alkene, so the proton that is adjacent to the double bond carbon, it is having the value 40. And in this case for alkyne, the proton close to the carbon, that is having the triple bond, okay, sp. So like that. So you can see depending on the functional group, also depending on the hybridization, how the pH or the pK value changes, right? So we need to find out the factors that govern the stability. So let us do that one. Yeah. The factors governing the stability. Right? So there are some key factors. Strong acid makes weak conjugate bases. Okay, so can have some comparison. So in between this H3O plus hydronium ion and H2O. Okay, so you have the difference. The pK value is -1 and this pK value is 16. Okay, so the general rule of thumb is that less pK value, okay, more acidic. Okay, like if you know that H2SO4, HNO3, okay, then HCl, this kind of strong acids typically have pH or pK generally 1 to 2, like that, very slow, or very less pK value. And whatever you have this bases like RNH2, then the tertiary MnR3N, so these are all having pK, okay, more than 20. Okay, like that. So less pK value means more acidic. So in this case, you can see this hydronium ion H2O plus, that is much more acidic than water. So what will happen if they lose the proton? So from here it will go to water if it loses a proton, and from there it will go to OH minus pK, I think around more than 35. Okay, so then you can see that this H3O plus hydronium is much more prone to lose one proton to go to the water. But while water is not that much prone to lose the proton, so you need some good nucleophile, okay, to abstract this proton, right? So then you can compare between some other molecules also, like if you have phenol, which, so this is having pK 10, and then you will have the ketone. Okay, this is nothing but acetone, okay, and it is having pK of 20. So if you just lose the proton, then what will happen? You will have negative charge, and this negative charge can go on and on inside the ring, and it can give resonance structures. So it will be very much stable. But in this case, if you lose it, then you will have this minus here, and this can go, but less resonance structures. Also, the negative charge is on the carbon, and here it is on the oxygen. So already I have tell you that the negative charge, it prefers to stay on an atom that is more electronegative. Okay, that is why this pK value will be little more higher. So it will not tend to lose the proton, but this phenol will tend to lose the proton. Okay, it can lose the proton. Okay, so this is the first case. Then you will have um, yeah. So same thing I discussed that electronegativity. activity of atom holding the holding the charge is important. Okay. So second thing is that size of the atom holding negative charge is important. Okay, so let us compare between water and hydrogen sulfide. Okay, so in this case, water has pK value of 16, but this has 10. Okay, so why is that? Because this OH minus, if you lose one proton from here, and if you lose one proton from here, it will give SH minus. So this is OH minus, this is SH minus. So sulfur in term of size is greater than oxygen. Okay, so this electron can stay much more. So in this case, let write it. In this case, electron will stay uh, far from the nucleus. Okay, and in this case, oxygen size is small, so its orbital size is also small. So electron will stay close to the nucleus, right? And what else? Electron will have more space to stay, as this is bigger in size. So the space available for electron is less. So this thing we also considered as diffuse. So that is why this pK value is less. So H2S is much more acidic than water. Okay, because in SH electron is having much more area to stay in the space. So for the same reason, you have some halide HCl versus HBr versus HI. So you know that all of them are having strong acid. HCl is strong acid we use in the lab. Then HBr is even stronger than this, and HI is even more stronger. So the pK value, if you see the comparison, HCl will be -7, HBr is -9, and this one is -10. So as I tell you, less pK, more acidic. So you can see that HI is much more acidic than HBr than HCl. So Cl minus, after losing the proton, this is Br minus, this is I minus. So I minus having much more, bigger in size. Bromine is less than that, fluorine is less than that. So that is why electron is getting much more space to roam in the space. That is why electron is much more stabilized in I minus in a conjugate base. So this is much stable. Okay, that is why the pK value is less, right? Then the third point is delocalization. Localization of electrons, right? So that is called plus M minus M effect or resonance effect. So as I told you, for the case of phenol, if you remove this proton, then what will happen? Minus H plus will have a negative charge here. Okay, let me draw in the next screen so that you can have more space to draw. So this O minus, first it can go here and this will go here. And we'll have something like this, negative charge. So remove, then this can go here, this can go here. We'll have, okay. Now, similarly, you can move forward. So we'll have, and now to go back to the previous structure, you can get back to where you have started. Okay, O minus. So all these things, okay, you can consider as, you can draw a resonance hybrid like this. And here you have, now you have del minus, del minus, del minus, and del minus. Okay, so you can see this is much more stable. In the comparison, if you consider the same thing without the delocalization, like the cyclohexane OH, and now you deprotonate it, minus H plus, okay, it will go, and you will have this O minus. But now you can see you can have nothing to do. You cannot break any single bond in case of resonance. And that is why you have the pi bond here. So no resonance possible. Okay, that means not stable. So that is why this phenol is having more acidity than, sorry, the cyclohexanol. Okay. Now another effect that is called inductive effect. Also minus I plus I effect. Inductive effect operates through sigma bond. Suppose you have two groups connected. One is RCH3, one is RX. So you know CH3, right? It can push the electrons. Okay, so it will increase the electron density of R. Increase electron density, but X, it is electronegative. Okay, del minus. So it will take away the electron through the bond. So this will reduce electron density. This is called plus I effect, right? This is called plus I effect. This is called minus I effect. Okay. So how does this change your pK or the acidity basicity? So let us try. This is a regular acetic acid. You have pK 4.76. Now you change the substitution. So you're introducing here you have CH3, right? Now you change it CH2, then which this pK is 2.86. If you change it more, Br CH2 OH, you have pK 2.9. You have fluorine CH2O OH, you have pK 2.59. Okay, so you can see that when you are having electronegative groups at the end, okay, it can take away the electron. Okay, it can take away the electron. So what is happening here? So earlier you used to have this resonance hybrid, right? These resonance hybrids you had. But now, as a whole, your electronegative substituents are taking away electrons. So this stability will be gone. Okay. So in this case, electron density will be pulled by the electronegative halogens. So that is why they will be much more prone to abstract. So this will go much more faster because you can you can adjust extra electron density. So earlier you only had sorry earlier only plus m. Okay, minus, no, this is not minus m actually, this is plus m, only plus m effect. And now plus m plus m, and this is minus I. So that is more stabilized. So that is why this pK value goes down even more, and you have a stable conjugate base. So let us move to other one. So which point was 3? This was 4. Now I'll discuss 5. Stabilization due to aromaticity. So in case you have two different compounds, these kind of questions generally come in competitive exams like NetGet. So this is pK value 20, but this has pK value 61. So you can say this is much more acidic, this is less. So why is that? So if you try to remove one electron, one proton, so suppose this proton I am removing, then we'll have a negative charge here. Now you calculate the total number of electrons. So here you have two, and one negative charge means two electron electron pair. So this is also two. This is acting like a 4n plus 2. That is aromatic system. So it can resonate in the ring. While this one, if you remove one proton from here, what will happen? This negative charge will come into the top, and now you can check total will be 2 plus 2, that is 4, and that is matching with 4n. 4n stands for anti-aromatic. Okay, and from our basic knowledge, we know that anti-aromatic systems are not stable. Hmm? So that is why, as this is not stable, its pK value is high. This is stable, pK value is low. So this will be much more acidic than the trinuclear one. This was 5 and 6 will be electrostatic effect. What is electrostatic effect? So this is a kind of molecule. So if you remove one proton from here, because H2 H, if you remove this proton, then you will actually get this species. Okay. These type of compounds are called halide. Okay, halide are compounds where general electronegativity is reversed. Okay, look closely to what I am saying. So carbon versus phosphorus. Which one is having, more electronegativity? I think phosphorus, right? Phosphorus coming same with, nitrogen group. Okay, nitrogen is having more electronegativity than carbon. So it will be del plus, phosphorus will be del minus. So what is expected? It will bear the negative charge as it is more electronegative, and this will bear the positive charge. Is it happening here? No, you can see that carbon is bearing the negative charge and phosphorus is bearing the positive charge. So this is special kind of compounds that are called halide. There are some reactions that you take the help of halide reactions. So this can also be present as pH and phosphorus pH and double bond CH2 like that. Okay. So here, if you lose one proton, then it will be stabilized because it will form a halide. Okay, so this is stable. So you can see this is a electrostatic effect, positive and negative, huh? And that is why it is getting stable. So these electrostatic effects also help, to stabilize the acidity or making the molecule more acidic. Okay, fine. Let's move to next. Now we have to discuss something about the basicity of compounds. So you already had a deep discussion about the acidity. So what is basicity? Basicity is basically the you know uh, effective 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 capturing of protons by a base. So it is a property of base that how good it is to capture a proton. Okay. Or you can consider it based on the different concept we discussed, like Bronsted Lowry. Okay, then you have your Lewis concept. So Lewis concept, you don't have any proton in that, so you deal with electrons. Lewis acid that takes the electron, and Lewis base give away the electrons. Okay, like that. So you can have this idea in mind. So suppose a species uh, gives proton. Okay. Second case, accepts electron. This can be considered as acid. And then species that one more thing. So it can also accept with minus. This you can also consider. And what else? So for species which can take proton, give which minus, also give electron. This can be considered as base. Okay, this is a shortcut trick that you can remember in any reaction scenario. So we know that basicity is the effectiveness of a compound that can capture a proton. So for example, For example, you have a base in a NH2 and you are reacting with the acid. So what will happen? The acid will be, the proton will be extracted from the acid. So you have your lone pair here. This is not lone pair actually. This is negative charge. The sodium is so, sodium is positively charged. Okay. Then you have this HCl, H plus, Cl minus. It can take away the electron, and then you can have this Cl minus and Na plus. It can combine to form the salt NaCl plus NH3. Now it can consider, we can consider as lone pair. So this pKa is 35. Okay, and now uh, this ammonia NH3 in presence of HCl, it can also react to form NH4 plus Cl minus. This pKa is 10. So when this will happen, in presence of extra HCl, in presence of excess HCl, right? And how your basicity uh, depends like on different factors. So if you have two compounds, one is this one, and so what is the difference here? You can see that you have number of carbon atoms is different. Here you have only one spacer. Here you have one, two, three carbon spacer. So what I am trying to mean is that your electronegative group, this is electronegative del minus, it is close to your amine group, but in this case it is far. So in this case minus I more, in this case no minus I effect. So how that will affect, how that will affect the basicity. Basicity I already tell you that there will be some proton and this amine will take that proton. So it will form CH, Cl3C NH3 plus. And this one, if you put H plus here, so it will take this H plus and it will become Cl3C NH3 plus, right? So this one having pK of 5.5, this one having pK of how much? 10. Okay, so what does it mean that pK 5.5? So this is much more acidic. Acidic means is conjugate base, that is this one, our starting molecule is stable. Okay, and pK 10 means its acidity is less. Okay, that means its starting molecule, that is the conjugate base, is not stable. Okay, so this one, the reactivity is less, reactivity is more. So you can see the difference here. Your electronegative group is taking away this electron density. So this is getting stable. So it will not form this one. Okay, the product. But in this case, here it cannot take the electron because it is far apart. So electron density is much more, it can go for the protonation, and that is why it will form this one, the protonated species. Okay, am I able to convey? Did you understand?
Yes, sir.
Thank you. So uh, next thing we'll discuss the acidity of amino acids. So amino acids are, so I will represent as a double amino acids, are very special in human body that are involved in many of the uh, protein processes. Okay, and what are the typical amino acids you have? You have 20 amino acids, if I'm not wrong. Okay, so many of them are essential amino acids. Okay, like that. And the thing is that pH is much more important to have a specific form of, sorry, yeah, specific form of amino acids and its motion. Why? Because we know that amino acids are typically of this type. So they have NH2, hmm, then some group, and then C double O H. They have both amine as well as carboxylic acid functionality. And you already know that uh, this amine are NH2 and are C double O H. They are different acidity or basicity. So their pK value is also different. pK value different. So in order to in order to stabilize them in specific form, we need to stabilize the pH value. Hmm. So like that. So many of the systems which will have amino acids that have the organic component, like let's say this one imidazole. You can also have histidine. This histidine is a part of the amino acid residue many times. So here you have one group R, and now if you give, so here you have lone pair, here also you have lone pair on the nitrogen. Now if you give some H plus, what will happen? Either this nitrogen or this one can take the nitrogen, sorry, the proton. So you have two scenario. One scenario you can have um, is positive, and one scenario you can have the other one. Okay. So you can see that in this case, this bond can move. Okay, and you can have some resonance structures. Okay, but in this case, there is no possibility because uh, only you have sigma bonds here. Sigma bond you cannot break for any resonance structures. So this one will be unstable. This one will be relatively more stable. So I will not consider it as stable enough, but relatively okay stable. So that is why it is more possible to protonate at this nitrogen atom. And on the whole, suppose you have R, NH2 and C double OH. So typically the C double OH has a pK around you know 2 2.5 like that, and NH2 you will have pK around 9 to 10. So depending on the pK, depending on the pK of medium, the specific form is table, right? So let's say it is having pK 2 and this one is 9. Now I am having scenario 1, case 1, pH is 10. Okay, so 10 is more than NH2 pK and your carboxylic acid pK. So it will stay as the form will be R NH2. This one will be COO minus, right? So if you have H2, your pH is 1.2. Okay, 1.2 means it is less than all pK. So then your compound will stay as NH3 plus COOH. Okay, right? And case 3, if I have something in between, pH equal to say 4. So pH 4 is less than NH2 pK, so it will stay as NH3 plus, but it is more than carboxylic acid pK, so it will stay as COO minus. So now you can see uh, overall charge how much? -1, right? Here overall charge how much? +1. In this case overall charge is what? 0, right? And this specific case is called as what we call as Zuiterion. Yeah. You have already heard of the term, right? Zuiterion. So in any species which will have positive as well as negative charge separated by some distance, okay, this will uh, considered as Zwitterionic form. So this depends on the pH. If you know something about protein chemistry, these things are very important to know the reaction mechanism of the proteins. Okay, or the functions. So this is one thing. And now relation of pH of a buffer solution. You know what is buffer solution? So buffer solution is prepared to maintain a certain pH. Okay, buffer solution is prepared to maintain a certain pH, and how do we prepare the buffer? So prepared by taking an acid and its, so we have to write in the next line its corresponding salt. Okay. So like you can have sodium acetate, sodium OAC, acetic acid buffer. So main thing is that you need to have a acid, and mostly it is a weak acid, and then you can take a salt, okay, salt with similar conjugate conjugate base. This is the general thumb rule to create a buffer. So in our body to maintain the pH, the pH buffer is used carbonate bicarbonate buffer. Okay, so HCO3 minus. Not sure of the form, but I'll check it. So HCO3, C3 minus buffer. Maybe it can be the other way also, that the carbonic acid and bicarbonate buffer, but I have to check it. So this actually we use in our body to maintain or preserve the pH. Otherwise, our body cannot perform. Okay, our digestion and all the other general processes is stable in this pH. Otherwise, we cannot survive. So that is one case, and to determine the calculation is the equation is Henderson Hasselbalch equation, and write the formula pH equal to pKa plus log of A minus and HA. So A minus is actually the salt concentration, and this is the acid concentration. Okay, and so there is a relation between these two percentage of the acid and percentage of the salt A minus. So you have somewhere in between 50%, and in this position your pH is equal to pK. Okay, so when your pH will be equal to pK, if this one is 0, right? So when this one will be 0, log of what is 0? Log of 1 is 0, right? So then A minus concentration equal to HA concentration. Okay, only when this both will be 50%, 50%. So when concentration of HA and concentration of A minus will be same, then this part will be 0, pH will be equal to the pK. But generally this doesn't happen because you have some dissociation limit of your acid. This is called a acid dissociation degree of dissociation, okay, alpha. So based on that, you have either less or more, like that. You have weak acid, you have little bit strong acid. So depending on that, you can calculate your actual pH, right? Uh, Now this is okay. I think that's okay. We have discussed the concepts, and then we can try to go for some question solving. Yeah. So We'll try to solve some questions. So this is from the practice set that has been given in this week. No, that will be non-graded. So here are five compounds that have been given, and it is told to arrange these molecules in the order of increasing acidity. Okay. So did you already solve the questions, or we can try it? It's from the practice set of the week. So let me just try it. So this is phenol. We already know that pK is how much? 10, right? Then this is OH2, similar to H3O plus. So this pK is -1, right? Here you have sp3 protons. Either you can consider this one or this one. Both are sp3. Okay. So this will have much higher pK value. So let us keep this one separate. We'll try to do the other one. Acetic acid, you have pK equal to 4.67, and this is alcohol, same as water, so you have pK equal to 16, right? And for sp3 or methane, like that, so similar as methane CH4, you have pK around 50. So what we have learned that less pK value, okay, more acidic, right? This is the relation that we have seen. So let me figure out then which one is having the less pK. So this one, 2 will have much higher. Then after that, we is having acetic acid, okay, 4. Then after that, 10 phenol, 1, okay. Then who is having alcohol, 16, so that is 5. And then who is having 50, that is 3. So anyone is having, any option is having this one, 3, 5, 1, 4, 2. Yes, yes. So this one will be the right answer. Okay, did you get it?
Yes, sir.
Okay, so I am not going into the detail because less pK value means more stable conjugate base. So I did not go into the detail. This is already discussed in the class. So just for shortcut, less pK value means more acidic, like that. Now, second question, amino acid glycine structure is given here. NH3 CH2 COOH has two acidic hydrogen. One is with pK 2.34. That must be this one. No, sorry. So let's the acetic acid. This one. Another with pK 9.6. This will be the amino. So what structure of glycine predominates at a pH of 12? Well, this is very easy. So 12, that is much more higher than all of the pK. So it will be on the basic form, right? So basic form means NH2 is going to stay as NH2. Then you have CH3 and COO minus. Something is available is C. This one will be right answer. Okay. So we move on to next. It is said that buffering is used to maintain the pH of human blood relatively around 7.3, 7.4. Just now I discussed. So which acid base pair serves to buffer the blood? So what will be the answer? Okay, this is carbonic acid and bicarbonate. So as I told you, I had some confusion earlier. So yeah, in this case, so this will be not bicarbonate carbonate. This will be, okay, carbonic acid and bicarbonate. This will be the actual buffer. So I got it solved from the question itself. So this one will be the right answer. Okay. So next question. So as per the Lewis acid concept, okay, a base is a substance that accepts proton, donates proton, accept a pair of electron, donates a pair of electron. What will be the answer?
Except protons.
Sorry?
Except protons, sir, first one.
First
No,
one.
no, no. You got a mistake. So what I told you, Lewis acid is concept where proton is not available. For protons we have Arrhenius and Bronsted-Lowry.
The answer third.
No. So let me just rewind you through the last part. So where I have discussed it. Yeah. See. So species which gives proton, okay, accepts OH or accept electron is called acid. This 1 and 2 as per Arrhenius and Bronsted, plus this, sorry, 1 and 3. And 2, this point is considered with the Lewis concept. Let me just go back to my previous slide. Here, just see it. Arrhenius, okay, Arrhenius is concerned about the proton. Bronsted is also concerned about the proton, but Lewis is concerned about the electron. A species which will be acid, it can take the electron. BF3, aluminum chloride, which have incomplete octet, they can take the electron. That is why they are Lewis acid. So simple trick is that you just remember this one. If any species is giving electron, that giving proton, that means it will take the electron. Okay, these two are opposite. So electron is negative charge, which is negative charge. This will behave same. Hydrogen or proton is positive charge and electron is negative charge. This will be opposite. So if something is giving proton, it will take electron. If something is taking proton, it will give electron. Okay. So something that is taking electron, it is acid. Something that is giving away electron, it will be base. Okay. So generally people do this silly mistake while considering Lewis and other methods, Bronsted or Arrhenius method. So that is a simple technique that you can use. Proton positive, electron negative. So this will be opposite. If something is giving proton, it will obviously take the electron. Okay. So as per Lewis acid concept, base will what? Base will take the proton, it will give the electron. So donates a pair of electron. Did you understand? So just let me know that if you have any confusion, I will describe it once again. Now, which of the following could be added to a solution of sodium acetate to produce a buffer? I have already told you, right? So you have a weak base, sorry,
Yes.
weak acid and salt with same conjugate base. So you have the salt here, sodium acetate. So you need acetic acid only. Okay. You cannot add any other hydrochloric acid or other salt or anything. You only have the same acid. Now moving to the next question. Arrange the following in the order of increasing acidity from least to most acidic. Okay, so can you try it? So there are two things. Okay, so one is resonance effect. Just a second. Resonance effect. Another one is inductive effect. Okay. Now we need to know that if both are present, okay, if both are present, then resonance will predominate over inductive effect. Because what is resonance? If you have any idea, resonance is actually, changing the electron position. Okay, electrons are actually changing the positions. These are delocalizing. But inductive effect, in this case, electron are not changing the position. It is just a push and pull effect through the bonds. So that is why resonance effect is much more, powerful than inductive effect. So if you have both, then resonance effect will be much more. Now I will try to draw the conjugate basis of all the species given here. This one, this one. So, right? Now, in which case you expect to have some resonance? Which case? Out of these four, which case there will be resonance?
Option number 3, sir.
Option number 3, because it has a conjugated double bond. None of the other option are conjugated double bond, right? So it can go here and this can be transferred to here. So what we will have? You have negative charge here and this one. And this can even go back. So you can, have this stability. So you can see this is much more stable. This is having resonance, but other ones doesn't have any resonance. So we know that this will be most stable. That we are clear. Now we have to think of the other species. So as we have ruled out the resonance, only we have the inductive effect. Now we need to compare 1, 2 and 4 in terms of inductive effect. Okay. So what is inductive effect? So I told you that plus m and minus I stabilizes the negative charge. Plus m is like this one. So your electron will move to the system. Okay, this is called plus m. Minus I is when something is taking away the electron density. Okay, this is called minus I effect. You can see here in this case, all the carbon atoms are sp3 hybridized. sp3, here you have sp2, and here you have sp. So based on the hybridization, what is your idea? sp3 is having 25% S character, sp2 having 33% S character, and sp having 50% S character. And having more S character means having more percentage of S character means close to nucleus, right? So this will, be much more electronegative because these are not diffuse, these are compact. S is, spherical in shape. It is close to nucleus, so it will attract the electron more. So 4 can attract electron much more, okay, than 2 because it is sp2, then 1 because it is sp3. So now if you just take the comparison, 4 will have much more stable than 2, than 1. So these three are considered for the minus I effect, and this one plus M effect. What is the answer then? 1, 2, 4, and 3. This one. Okay, did you understand? Am I able to convince? Hello?
Yes, sir.
Hmm. So first you check that if any resonance effect is available or not. If resonance is there, it will prefer, it will predominant resonance. Then resonance ruled out, then you go for inductive. Now you check that which one is most electronegative. Huh. So in this case, depending on the hybridization, you can see that more S, that means more electronegative, it will take away electron. Ultimate thing is that you need the stability of the negative charge. How you can stabilize it? If you think systematically, you can get to the answer. It's very simple. Next question, it tells that which of the conjugate bases below is the strongest base. So can you try it? This one, strongest base. So basicity, as I told you, depends on how unstable the lone pair or negative charge is. Why unstable? Because if you stabilize it, it will never going to act as a base. Why it will go? It will go to take away our other proton because it is already stable. So it should be unstable for basicity. Now check it. So you have four compound here. This is phenol. So this one, this negative can be stabilized over the network. You have one electron withdrawing group here. This is electron withdrawing group. Okay. So this one you have OCH3, that is electron donating group. Okay. And this one you have methyl group. This one also electron donating group. What you can understand that this you have plus M effect. You have a nitro group here. So nitro group electron withdrawing, so it can take away the electron. So you have plus M and minus I both. That is all stabilizing your negative charge. But in this case, you have electron donating group. So electron donating group unstabilize. Sorry, not unstabilize, destabilize. Destabilize. Now you have to check that which way it is destabilizing. Is it inductive effect or is it resonance effect? For methyl, it doesn't have any lone pair present. Okay, it can only have this inductive effect, that is plus I effect. So it will push the electrons through the bond and it will destabilize this negative charge. But here, this oxygen, it has lone pair also. So it can give the resonance effect. It can give minus M effect. It will come to the oxygen. So this one is most destabilized. So now you can see which one will be have most basicity, most basic. Which one?
Option 3, sir.
Option 3, because it is most destabilized. Destabilized. So you can always remember that for acidity, conjugate base should be stable. For basicity, this is not about conjugate base, so the or okay, if this is conjugate base, it will be under conjugate. Okay. conjugate base should be unstable. For basicity, it should be unstable. For acid, it should be stable. So this is already having the negative charge. That means it is conjugate base, right? It will take the proton. It will take the proton and then it will go BH plus. This is your conjugate acid. But this one is conjugate base. These all are conjugate base. So for basicity, conjugate base should be unstable, but for acidity, it should be reverse. Okay, did you understand? So we will go to the next question. It is not going. Just a second. Oh, just a second. Yeah. Yeah. Just give a minute. My connection is there, right? You can hear me. There is some network issue. I think this one has gone. Can you hear me? I'm audible, right?
Yes, sir. Audible, sir.
I had some network issue, so that is why this has gone. Okay, I'll write it once again. This one is having electron bonding group. Is also electron bonding group. This electron neutron group. Okay, then activity is having minus M effect. That is having plus I effect. These are all conjugate bases. So this is the right answer, most unstable, and that for acids conjugate base would be stable. For bases conjugate base would be unstable, right? So we'll go to the next question here. So it says that the given amino acid, aspartic acid, okay, is titrated with sodium hydroxide. At what pH all the amino acid molecules will have a -1 charge? So you have two carboxylic acid part and one amino acid part. Okay, so now you have to check that at which given pH values, at which pH it will have -1 charge. So let us try all the scenario. So case 1, pH equal to 1. pH 1, what will happen? So 1 is less than every pK value. So 1 will be in the protonated form. So it will stay as which, then NH3 plus, then which. Overall charge is how much? Plus 1. Go to next one. pH is 3. So it is less than this carboxylic acid, so it will stay as protonated form, which it is also less than this one, NH3 plus, but it is more than this one, minus. So now overall charge is 0. Move to the third one, pH is 5, so it is more than this two, but less than 9.6. So these two will stay as minus, NH3 plus, and O minus. So overall charge is -1, and for the fourth option, all the groups will stay as the depolarized form. So here overall charge is -2. What is the answer here? -1 charge at pH 5. Right? This is very easy. So for the amino acids, we'll take one more slide here. It's very important. So this is not discussed actually. For amino acids, since you have pK1 and pK2. What is pK1, pK2? Like suppose you have like in this case only. So I'll draw it one second. OH, NH2, OH. So this one you have pK suppose 2. This one you have pK suppose 4. And this one pK suppose you have 9. Now, if you someone is asking you to calculate pK1 and pK2 values, okay, so it will be like this. pKa1 will be just a second. So there is a relation actually. So these are three pK values. So one is called pK1, I think, which is the least one. Then pK2, okay, middle, and pK3, okay, the most. And then you have to calculate the pH value. So pH value is and to check it might be okay. We'll discuss it in the next class because there is some relation like pK1 plus pK2 by 2 like that. Okay, I don't remind it this moment. So I will discuss it in the next class for amino acids. You have two different pK values. So just let me wipe up this one. Yeah. So which of the following has a pH greater than 7? Can you try it? We have vinegar. Vinegar is basically acetic acid, CH3COOH, that has pK around 5. You have lemon juice, okay? It is also acid. So basically it will have pK less than 4. Gastric juice, that is in our stomach, so it is also acidic. HCl is there, so it is having pK less than 5. Only blood plasma, okay? So this is having pK greater than 7. Also, which of the following? So it will be the right answer, blood plasma. All the others are acidic. So we go to the next part. An acetylide anion is an anion formed by removing the proton from an end carbon of a terminal alkyne. Which among the following bases can deprotonate a terminal alkyne to generate acetylide anion? Okay, terminal alkyne R C not H. This is called a terminal alkyne. You have some R group substituent groups present, and on the one terminal you have an alkyne group. And this is the proton that it is being discussed here. So you have to remove this one. So you know that for alkyne, pK is how much? pK is 25. So it will not come out that much strong because it is less acidic. pK value is much more. So you need some strong base. Okay. Need some strong base or nucleophile to abstract the proton, right? So normal, like uh, this sodium hydroxide, okay, then this NaOET, this is called NaOET, sodium ethoxide or sodium bicarbonate. These are not strong enough. These are not strong enough to uh, abstract this proton. So do you know what is this? This is called Grignard reagent. Have you heard of it? Grignard reaction. This is called organolithium reagent. Yeah. These both are same organolithium reagents. So why these are much more stronger, nucleophile because of this metal part. This lithium or magnesium bromide, okay, these are working as positive. Okay, there you can see positive, and this part has the negative charge. You are having either nitrogen negative or carbon negative. So these are so strong. Okay, very strong nucleophile, so that it can abstract any proton. Okay, so this kind of CH proton or NH proton, okay, this can be abstracted by this organometallic compounds. Hmm. So this 1, 2, and 4, all three will be uh, able to abstract in the proton. So you must have heard about butyl lithium, right? 1, 2, 3, 4 minus lithium plus. You all have heard about butyl lithium, right? This is so reactive, catches fire in air. You cannot expose this, compound in air. It will catch fire immediately. It is so reactive. And also the reaction temperature, reaction temperature is minus 77 degree Celsius. You see how low. So if you react this one in room temperature, it will be vigorous reaction. It will be explosive reaction. We cannot use this one in the lab in room temperature. We have to go to the low temperature. This is that much strong reagent, butyl lithium. So that's what this organometallic, organometal containing compounds. These are very good nucleophile. It can abstract any proton you want. So just a second. Yeah. So we'll go to the next question. Complete the reaction given below. How many questions left? 2 3. Complete the reaction given below for the acid-base reaction. Which species would exist in majority in equilibrium? So let us complete first. So as I told you that butyl, not butyl, the organolithium containing compounds are very strong. So it can abstract the proton. So which proton? This proton it will abstract. This minus charge, it will take this proton and this electron will come to the oxygen. So you will get O minus, and this will be stabilized by the lithium plus, right? And this one you will get the CH3 methyl toluene. Okay, now you have to check that which one will exist. So as I already told you that this is very reactive. This is very reactive and unstable. Compared to this will be stable. Okay, so to justify the stability, so as this is stable, so concentration is more, so it will be forward direction. the reaction will move to forward direction. So which species would exist in majority at equilibrium will be product. So now let us understand the reason behind it. Two things you can consider here. So one is which. So in our understanding, we can consider this pK value. pK of which is 16, and this one pK value is 50. Okay, so now if you consider the K equilibrium, that is 10 to the power, pK value of right side, that is 50, minus pK value of left side, that is 16. So you have around 10 to the power 34. That means that your equilibrium constant is so much higher, so it will favor forward reaction. Okay. And let us understand that what is the reason. So here lithium is a hard uh, lithium is a hard center. Okay, so lithium is very small in size. So if you compare between sodium and lithium will be hard center. But this carbon is soft. Why? One thing is it is less electronegative carbon. And another thing is that this negative charge it can delocalize. It can be stable. So it is soft center. So hard soft interaction. Compared to here, oxygen is much more electronegative, smaller in size. So this is also hard, and this is also hard. So this interaction can have some effect. Hard interaction is stable. This is one thing, and hard interaction will be more effective than the hard soft interaction. This you can consider, and depending on the K equilibrium constant value. So two things that you can consider here. Okay. Moving to next question. It has been asked that the K equilibrium for the polymer reaction is of the order of. Okay, so just let us see. This hydronium ion pK is -1. And here you have this one pK is what was the pK for? Okay, pK is 10. In H3 you don't have any pK for this one. Okay, so you have to understand one thing. So K equilibrium is equal to 10 to the power pKa of conjugate acid, okay, minus pKa of acid. Okay, so this acid is in the left side. So the derivation of this equation is already discussed in the class. So I can take one more slide to discuss it. Okay, just a second. So pK of conjugate acid is this one, 10 to the power -1 minus pK of acid. This value is 10 to the power -11. So this one is the answer actually. So why we are not considering the water? So that I will tell you while derivation. Okay, so this is the next one. Rank in the order of acidity of indicated protons, least acidic to most acidic. Okay, so what will be the order? Any idea? So this one is having the proton that is connected to a carbonyl group. So if you lose that proton, then what will happen? You will have uh, just a negative charge will be here, then oxygen, and then this one. But these will be much more unstable. Stable. Why? Because carbon. So as oxygen is delta minus electronegative, this should always be delta positive. Okay, this cannot bear any electron. This is much more unstable. Compared to this one, if you lose this electron, then it will be minus. Okay, this will be stable because it can have some resonance effect. And then you have here, if you remove this proton, you have negative here. It can also have some negative effect. But in this case, you have also chloride inside that can give. So plus m and minus I is here only plus m. So this will be more, right? And then if you have this one here, so if you remove this one, CH2 minus, you can also have the similar resonance effect. Okay, so the least acidic will be 4 because it is much more unstable, the conjugate acid. Then it will come 2. Okay, because just a second. Yeah,
Option 2 and 4 correct.
2 and 4. Actually, yeah, this is given same option, right? Between 1 and 3, you know that here both plus m and minus I are there, so it will be having much more stability than 1. And for 2, we have to check it. These 3, okay, so you can consider it like this way. CH2. So if you take this electron, this negative can go here and give the resonance hybrid. Okay, so both these two will be the right answer actually. Yes. And then I will tell you how we derive this equation so that you can get to the value, because this is required. Yeah. So suppose you have this equation HA plus B. So what you are having? So this is a base that will abstract this proton, and this electron of the bond will come to A. So you will have BH plus and A minus, right? This is acid, this is base, this is your conjugate acid, this is your conjugate base. What is equilibrium constant? K equilibrium is product concentration by reactant concentration. What are the products? BH plus, A minus. What are the reactants? HA and B. Right? Now, let us do one thing. K equilibrium into 1. We are multiplying 1, but here what we'll do? BH plus A minus HA and B. Here what we'll do? We'll multiply this one, H plus ion concentration, both on the top and the bottom, because it is basically meaning 1. Okay, so now you can see that if you're going to redistribute, then A minus into H3O plus by HA into BH plus H3O plus into B. But you can understand this one is actually your uh, dissociation constant, okay, for HA. So this is dissociation constant for your acid, and this one, if you just consider it as 1 by this one, you can consider it as, I'll just write it. So here minus H3O plus HA into 1 by H3O plus B by BH plus. It's the same thing, right? So this one you can consider as 1 by dissociation constant for BH plus. Okay. So that is actually K for HA, K for HA, and this one, sorry, more precisely it was KHA, and then this KBH. Okay. Now, if you take the log, so I can directly write as pK equilibrium equal to pK HA minus pK BH plus. Okay, and from there, I'll take one more slide. Just from there, what we can write, K equilibrium, we need to do the 10 to the power pK of conjugate acid minus pK of the parent acid. This you can check it. So that is why we are not considering, this water part here. Okay. So you can check it with yourselves. You can do the derivation, and then you can get back to me in the next class so that we can, discuss it once again. Meanwhile, I will also look into this. So two things. One is this part, derivation of this one, and another is pK1, pK2 value of the amino acid. So that thing will recapitulate from this class in the next, and then we'll move forward. So I think today it is already done for our class. So is it okay? Do you have any questions on this?
No, sir.
You can always check the material and tell me in the next class. Okay, that's not a problem. So I will upload this one so that you can have an idea. Okay, so thank you all. We'll meet in the next class.